Hello, physics class. I am wanting you to, I assigned worksheet 4 to you guys to work on today. That's going to be due next time in class. Now, I do understand that I'm not there, I can't answer questions and everything like that, but I do just briefly want to talk about, I'm going to work a problem with you guys here in a second, but I do want to take a brief little minute to review the quantitative things that we've been deriving in the labs. So, in the previous labs, the very first equation that we derived in terms of energy is the elastic energy equation, which said the elastic potential energy is equal to one half the spring constant times the displacement of that spring, how scrunched up it is, squared. Now, the whole purpose of that previous worksheet that you guys turned in that maybe you're feeling a little bit uneasy about is to figure out that the elastic energy is on a force of a spring versus delta x. When I plot that and I get a straight line, the energy is the area underneath that curve. It's really important. Okay? So anyways, the first energy equation that we derived in labs was this equation. The second one was we did the lab where we examined all the elastic energies being transferred to gravitational energy. We looked at the relationship between delta x and height, and we found that delta x squared is directly proportional to height. And through unit analysis, we were able to determine the rest of that must be like that. The gravitational potential energy is equal to the mass times 9.8 here on Earth, accelerated due to gravity times the height. And then finally, we did a lab where we transferred all of the gravitational to kinetic energy, and we found that the delta H is directly proportional to the velocity squared. And using unit analysis, once again, we were able to derive the equation to be 1/2 mass times velocity squared. So with that being said, we derived all of these equations, and then last time in class, we started working with LOL charts to help us come up with other equations. So with that being said, let's look at problem number 3. So, it's not number 3. This is problem number 7 on worksheet 4. So that's what you were just given. It's on the back side of the first page. Now, a lot of the ones on the front page are just simple plug and chug. It's how much kinetic energy does 20,000 kilogram traveling 70 miles per hour. That's kinetic energy, mass, velocity. Make sure the units are right. Just plug it in, solve. Number 7 is where it starts to apply what we've been doing in the previous class. And so it says we got a cart moving at part A here, point A. It's moving, it has a mass of 8 kilograms, and it has a velocity of 5 meters per second. Then it's going along here, it's rolling across, and I think we're assuming no friction. When it hits the spring comes in a little bit, and it says that the spring constant is 50 newtons per meter, and the velocity when it comes in and scrunches that spring all the way to its max, temporarily it's not moving, so it's got no velocity. That's point B. So then it asks us to draw an LOL chart. It doesn't tell us what to define our system as, but let's think about what we could define our system as. Well, we are wanting to know, we are going to have some kinetic energy because it has a velocity there. So we're going to want to make sure that the cart is included in our system. Well, also we got a spring constant here, and the spring's exerting some kind of energy, so I want to make sure that I include the spring. Also, it's probably just good practice to include the Earth, even though we're not changing our gravitational energy. Therefore, it wouldn't really matter if the Earth was in the system or not, because it's not really affecting. Same thing with the surface. I don't have to include that. The table surface, I don't have to include that in my system or not, because I'm assuming no friction. If there was friction, I would probably want to include it. So anyways, I've got that. Then I've got EK, the elastic energy, or gravitational energy is what they list next. The elastic energy. EK, EG, EEL. Now this is our A, this is at position B. So at position A, it's got some velocity. I'm not really dealing with gravitational throughout this whole thing, so I'm just going to ignore that. At the first part, it hasn't touched the spring at all, so it's got none of that. So therefore, I know I have kinetic energy. At that point, it's probably going to have the most it's going to have. So therefore, I'm just going to show 3 bars of kinetic energy. Well, then I come over here after, and at position B, and I notice that the velocity is 0. Therefore, there is no kinetic energy. In order for the law of conservation of energy to have been satisfied, all of that kinetic energy would have had to have transferred to elastic energy, just like that. So I've got that LOL chart. And that was really important because we use that information then to write the following equation. What the energy was doing before equals whatever it was doing after it. So in this case, we've got the kinetic energy is equal to the elastic energy. Well then, so that's B. And then on C it says to determine the maximum compression by the spring. When I look at this equation I just wrote, I'm like, I don't have any maximum compression of the spring. But wait a minute. Don't I know what the equation for the kinetic energy is? Right, so I plug that in. 1/2 mass times velocity squared. Then I'm like, oh, wait a minute, I got the elastic energy as well. That's 1/2 K delta X squared. And so one thing you'll notice about this, the 1/2s that are on both sides, you can save yourself a trip. Since they're up here on both sides, I can divide this side by 1/2 and they'll cancel. So I'm just getting rid of it. So basically I've got mass times velocity squared is equal to the spring constant times the compression squared. And so I know the mass, I know the velocity, I know the spring constant. It's just a matter of solving for delta x. And so let's plug in numbers. I say 8 kilograms times my velocity squared, which is 5 meters per second squared, should be equal to the spring constant, which is 50 newtons per meter times delta x squared. So to solve for this, I'm going to take 8 times 5, 25 squared, or 5 squared is 25. 25 times 8 is 200. And that should be equal to that times delta x squared. So basically I'm taking 200 divided by 50, and that's going to equal delta x squared. And so when I square root that, 200 divided by 50 is 4. So the square root of 4 is 2 meters. And I should write proper sig figs, so probably 2.0 sig figs, because those are all 2 sig figs up there. So 2.0 is the correct answer. The key thing about this is we're now using our LOL charts to write the energy conservation equation. And then we are substituting these equations that we derived in the lab to know how questions like